First of all, I would like to thank the organizers with AI Summit for giving us an opportunity to talk about our research. Here, I would like to introduce my student in our lab. Right. So, my name is Hien, and we work in Ho Chi Minh City University of Technology. International University and Ho Chi Minh City, Vietnam National University. My student, Hien Thư, right? She worked with the field of brain tumor. And next, Lê Xuân Hiếu, he studied with the field of malaria and leukemia. And the final student, Đạt, he researched in cancerous detection, right? Thank you again. So I will talk first, right? Thank you. So now I would like to introduce our research about detection and classification of cancer diseases utilizing deep neural network. For those who don't know me, I just introduce briefly. I graduated from Ho Chi Minh City University of Technology, Bách Khoa, right? And my major is mechatronics. And then after that, I get a master and PhD degree in Taiwan. Thank you. So we already introduced me, Hien Thư, Hiếu, and Đạt, our research group. So I move to the first topic, talk about summary. We have totally 4 topics. The first, we will talk about the breast cancer, how to classify or detect. And the second, we will talk about the topic to the thoracic diseases, 14 different of diseases. And then my student continue with brain tumor. And finally, Hiếu with leukemia and malaria detection. So I talk the first with the first topics, classification of breast cancers. Yield the histopathological image using the convolutional neural network. We already published in international conference. So you know the breast cancer, this is the most common cancer in the woman, right? And in 2012, we had 1.7 million new case diagnosis. And in 2015, had 570,000 women died from breast cancer. In Vietnam, we have 10,000 cases of the female breast cancer. So that's the reason why we try to apply the CNN to assist pathologists in cancer detection and give pathologists time to focus more the difficult cases. I think I just talked very briefly about the CNN model. All of you know this, right? And we apply the CNN model in our research. And in the CNN architecture, we use the VGG 16 architectures with some different players here. And actually, we also use the VGG 19 architecture for compare the results. And The other CNN architecture we use Inception V3, right? So the Inception V3 has so advantage to compare with the VGG16. And another model for CNN architecture, we use the ResNet 50. And in here, we choose the 3.3 matrix for the ResNet 50 architecture. So our data, we had the data, this the name ResHit data, and we download from the internet. Right? And it contains 709 7,909 microscopic images collected from 82 patients, and with different of the permanent and the malignant. Here, some example for the permanent. You can see a different of the magnification level 40, 100, 200, and 400 S, and this malignant sample. This is our model for reprocessing. We have two stages for the image level classification. We first to resize into this side, right? And after that, we had the image augmentation and retrain model. The other stage, we use the part 2, part session, and then again, image augmentation and retrain model. And this is results for the first topics. This is you can see here we had a comparison among the VGG16, VGG19, and the ensemble, right? 3 different. And here for the path-based classification, we also have compared between the Inception V3, different model, ResNet 50, and the ensemble. And again, we also had the other results. I continue with the second topics. This topic, we focus to radiologic level CAD to detect 14 thoracic diseases. And in here, we use the chest X-ray image, and with 14 different diseases. Here, some of the different diseases difficult to read, right? We try to detect and classify for 14 different diseases. And this is our model. Again, we use two-stage model. The first is segmentation. And we apply the UNES model and try to classification, apply the CHEFNET. And in here, we use CNN to classify 14 diseases of lung cancers. In here, we also apply with a glass activation map to show the map with the color for easy to understand with the doctor can read the image. Just the function we apply in the second topics. And here our results. This is some the different of the result. We try to segmentation, right? With a different of the lung segmentation and lung diseases. And in here we we have a result for compare between the ResNet 50 and the CNET 1-to-1, right? the red line and the right line here, right? And it's, you can see, it seems the redness 50 model is better than the denseness 1 to 1 here. And we apply with CAM to make some colors for the easy, the doctor can easy to see the lung diseases and focus to the difficult case. Here you can see our results. So with the image and the reduction, 14 different diseases and how many the percentage of different of diseases. So, okay, and the next topic, my student continue with brain tumors. Thank you.
Yeah. Hello, everybody. So this is my part, and now I will talk about my research: the automatic glioma brain tumor using machine learning. Yeah. As you know that gliomas is one of the primary brain cancer, accounting for 80% brain cancer all over the world. And as you can see on the screen that there are 3 glioma images of 3 different subjects, and the glioma tumor appear in the different size, different location, as well as the intensity. Hence, the structure is very complex to segment the subregion. However, segmentation of subregion is very important for clinical decision, and because manual segmentation is time-consuming and irreproducible, therefore, the automatic segmentation becomes more popular and get countless attention recently. In this research, we use the TS 2018 dataset, a public dataset containing multiple MRI scans of 2 types of glioma tumor. The first is the high-rated glioma, shortened called HCC, and the second is the low-rated glioma. And each sample containing 4 types of modalities: the T1 post-contrast, T2, and flare. And the raw truth contains, the raw truth includes 3 subregions. The subregion is manually labeled by the expert board using the number. As you see that the number 1 is for the whole tumor, number 2 is for the tumor core, and number 4 for the enhancing number. For better observation, I use the color to visualize the image using the ring for the whole tumor, the enhancing tumor in yellow, and the tumor core in red. Then in the pre-processing method, because the input of my machine learning is just a 2D data, but the data is the 3D scan, so I have to extract the slide over the ISO plane. And because the data raw is quite large, so the patch-based technique is very essential to reduce the computational expense. And then I put the data after pre-processing state into the UNet model, because the UNet model is a very popular model for segment the biomedical image. And the visualizations of the UNet model. And the results, you see that this is the raw data, the raw truth, and the prediction. And the accuracy of the whole tumor is the better than the enhancing tumor and the tumor core. However, for the filter work, if we use the 3D input instead of 2D input, maybe the result may be better. So, next slide, next part.
So in this part, I will briefly talk about the use of deep learning to detect several diseases in fluid microscopic image, such as malaria and acute lymphoblastic leukemia. So for several years, malaria and leukemia remain as the dangerous and common disease among all fluid disease, and the traditional method to detect those diseases is hematological image microscopy. However, this type of approach has several limitations. First, it requires expertise knowledge, and also it takes a long time to process and diagnose an image. So this is the motivations and raise the need for building an automatic tool that can conduct on the diagnosis and detections of those disease. So inside this conducted project, what we aim to do is to build a CNN and AI-based model that can not only perform the detections of those two diseases, but can also provide a more interpretable detections by locations and point out infected or cancerous cells. So I will talk briefly about the methodologies. So when a microscopic fluid mirror image is processed in the model, every single white blood cell and every single red blood cell inside that image will be isolated out, and all the white blood cell will be passed as the input to a white blood cell model that will somehow detect if that cell is cancerous or not, and similarly the same process goes to the red blood cell to detect malaria. So this is the performance and some demonstrations of our system. And overall, the common measurement reveals that this type of system is promising, and I hope that it can be used to reduce the labor effort and can give a second opinion for detections of the disease in several hospitals. And I will talk briefly about the Department of Biomedical Engineering. So besides those conducted projects which I have just mentioned before, our department also conduct on several related projects. For example, we conduct on the detections of eye disease or skin disease. And our department have raised enthusiasm to bring HI into the medical technologies. So we often hold frequent HI conference, such as the AI for Healthcare conference at the BME International University. And for those who want to contact or keep in touch with Dr. Hien Pham, please find this email address. And this also brings us to the end of presentations. Thank you for your attention.